I have two reactions listed up on the board right now. One of them is a fission reaction, and one of them is a fusion reaction. These are the exact examples that we went over yesterday, but that doesn't matter whether they are or not. Fission always takes the same form. Fusion always takes the same form. So even if you don't remember the exact reactions, it's okay. You can still identify which is which. Tell me the first one. Is that going to be a fission reaction or is that a fusion reaction? That's a fusion reaction. How do you know that that's a fusion reaction, Ollie? Eh, what stays the same? No. Yeah. There you go. That's exactly what you had in your head, right? Because two things are going into one. We've got two H2s. Now remember, it doesn't have to be H2 and H2 that are combining together, that are fusing together to form helium or whatever else it is. In the end, if two light nuclei combine, fuse together to form one heavy nucleus, that's nuclear fusion. Now, this neutron and this energy here, they're not important in determining what type of reaction it is. They're important for other reasons, but not in determining what kind of reaction it is. Bottom one, therefore, must be fission. We know that's going to be fission by default, but also because one thing becomes two. It splits apart into two things. Again, the neutrons and the energy here, they're important for other things, but not important to determining what type of reaction that we have. All right. We get energy produced in both of these. Energy produced right here, energy produced right here. Can you tell me if I have a single reaction of each of these, nuclear fusion, nuclear fission, can you tell me which one's going to be a bigger energy? Which one's going to produce more? Good. The fission is going to produce more. If we label these nuclear fusion, nuclear fission, if I have a single reaction, the fission reaction will produce more. But if you look at what we have, what kind of elements we have here, the fission has much heavier elements. So a single reaction involves much, much more mass in a fission reaction than it does in a fusion reaction. If you're not looking at an individual reaction, but rather you're looking at a certain amount of mass, an equal mass of hydrogen as compared to uranium, let's say a kilogram, which one's going to produce more then? In other words, which one produces more energy per kilogram of fuel? That one's going to be, Rosie? That one's going to be definitely nuclear fusion, right? So this one produces more per kilogram. This one produces more as a total for one individual reaction taking place. Does that make sense? If you got a kilogram of both, you're going to get way more reactions taking place here because each reaction involves a much lighter amount of material. All right, tell me where that energy comes from. Where does that energy come from? We talked about which one produces more energy per kilogram. Where does the energy come from? Somebody, can't remember, it was this class or the other class yesterday, said, well, doesn't that violate the law of conservation of charge? Or sorry, conservation of energy? We get energy from nothing? Well, it kind of does, actually. It kind of does. But how do we resolve that, Ethan? Yeah, binding energy. Yeah, and binding energy comes from a two-word answer. Mass defect, right? We lose mass. We gain energy, but we lose mass. So it's kind of like saying that energy and mass are two different forms of the same thing. Kind of like ice and liquid water are two different forms of the same thing. Let's say we used to have the law of conservation of ice and the law of conservation of water. Well, now we realize that, wait a sec, you can change ice into liquid water and liquid water into ice. Now we may actually lose ice. It's gone. I mean, we may lose water, but it's gone. But combined liquid water and ice is going to stay the same. If we look at more energy being created here, well, it's not really created, it just comes from mass. If we have more energy coming out, then we have less mass. We call that a mass defect. In the context of a reaction, a nuclear reaction, the mass defect is the difference in mass between what we start with and what we end with. Which one's going to be bigger? Which one's going to have more mass? Let's call it reactants and products, even though it's really parent and daughter. Which one's going to have more mass, the reactants or products? If we gain energy, then we must, Ethan? Yeah, if we gain energy, we got to lose mass. So that means the mass of the reactants is always going to be greater than the mass of the products. Therefore, we're going to have more energy on the right side than we have on the left side. Yep. Yes. The question was, if you didn't hear it, was if we can turn mass into energy, can we turn energy into mass? And the answer is yes. Just real quickly, and I don't want to go too far on this because um, we don't really have to know this, but just to fully answer your question. Um, how many people have heard of Einstein's theory of relativity? Okay, there's a special theory of relativity, and then there's the general theory of relativity, and there's a whole lot to both of those theories that I'm not going to talk about right now. Okay? You could do an entire course on more than one course on each of those. We're going to spend about 1 minute on Einstein's theory of relativity. One of the things that Einstein's theory of relativity says is that nothing can travel faster than the speed of light. Okay? How do you get something moving faster? Well, you pump energy into it, right? You want to make your car go faster, you get potential energy from the gasoline, it gets converted to kinetic energy. Einstein said that as you approach the speed of light, as you get going faster and faster and faster, and approach the speed of light, and then things actually get heavier. It's kind of weird, but like, put your foot on the gas pedal. Let's say your car was going close to the speed of light. Get your foot on the gas pedal. Your car goes a little bit faster, but it also gets heavier as your car goes faster. Now, the reason that that happens comes back to your question just a second ago, Peter. The reason that happens is because as you approach the speed of light and you pump energy into making something go faster, some of that energy doesn't go into making it go faster. Some of that energy gets converted to mass and makes the thing heavier. And as you get closer and closer and closer to the speed of light, then a higher and higher and higher proportion of that energy gets converted to mass rather than speed. So as you get closer and closer and closer to the speed of light, it becomes a much less efficient transformation of potential energy to kinetic energy, and a much bigger proportion of it goes to mass. So simple answer to the question is yes, you can convert energy to mass, and that's one place we could see that. Yeah. Uh, I'm gonna I'm gonna I'm gonna say no, but I'm gonna qualify that answer no, because you can't actually reach the speed of light. As you get infinitely close to the speed of light, then you get infinitely close to all of your energy being converted to mass. So you can never actually hit that speed of light. One more question here before we move on to the next page here. Nuclear fission can undergo what we call a chain reaction, because nuclear fission requires a neutron to bond to a uranium-235 to make it unstable enough to decay into krypton and barium. Then the 3 extra neutrons, or 2 or 4 or whatever it is in the particular reaction you have, end up combining with more uranium to cause more reactions to take place. So this ends up causing this. And each of those end up causing 3 more reactions, and so on and so on and so on. It's a chain reaction where the products of this become the reactants for more reaction. Tell me how fusion takes place. We fire a neutron at uranium in order for fission to take place, and then it sustains itself. Tell me how fusion takes place. What do we got to do with that one to get it going? And I'll give you a hint. It's not fire a neutron at it. Yep. Yeah, it needs energy. Why does it need energy? Why does fusion require in fact, a lot of energy to make it take place? Yeah, the hydrogen nuclei are both positive, and that force of repulsion gets bigger and bigger and bigger as they get closer and closer and closer together. So we have to have a lot of energy, usually in the form of heat, to overcome that force of repulsion. How does it sustain itself? We pump energy into this. Well, that's great. How does this reaction sustain itself? Or down here in the chain reaction, the neutrons caused more reactions with the uranium-235. Up here, some of the energy that's released causes more hydrogen to fuse together, and produce even more energy. And some of that goes into causing even more hydrogen to fuse together and produce even more energy, and so on. Does that make sense? So the chain reaction down here is sustained by the neutrons. The chain reaction up here is sustained by the energy that's generated, or at least a little bit of the energy that's generated. Is that okay? All right. We talked a little bit about mass defect on the previous page. You guys wrote this down yesterday, but I'll just quickly refer you to not mass defect of the reaction. We already talked about that, right? The daughter weighs less than the parent. The product weighs less than the reactant. And as a result of that mass defect, we have a certain amount of energy released. We call that the binding energy that's released. But in the context of a single nucleus, it's where it gets even worse, even more confusing. Okay? Just when we think we kind of get the idea of losing mass in a reaction and generating energy in a reaction, when we start talking about individual nuclei, and we see that if we add up all the pieces inside the nucleus, the mass of all those pieces, it doesn't equal the mass of the nucleus itself, which I don't know about you, but to me, that just seems so strange that we can take the mass of the parts and it doesn't equal the mass of the whole. The mass of the parts does not equal the mass of the whole. The mass of what makes up the nucleus is more than the mass of the nucleus itself. Where is it? Well, it's energy. It's stored as energy, as we call binding energy. Okay, and that's what ultimately allows there to be a mass defect and therefore an energy released in a reaction. So the mass defect in the binding energy of a single nucleus is what allows this to happen in a nuclear reaction. All right, I want to do a quick little example. Well, one of them is a quick little example, one of them not so quick here. But first I want to define a term here. We don't see this very often in Physics 30, but from time to time we do. You may have seen this in in Chemistry 30 before. An atomic mass unit. These are both units of mass, by the way. We're not going to look too much at what an MeV per c squared is. I just want you to recognize that that is a unit of mass, not a unit of energy. It's MeV per c squared. If you look at m is equal to E over c squared, E is equal to mc squared, right? MeV, energy, over c squared. This is a unit of mass, not a unit of energy. This is one we want to spend a little bit more time on, though. An atomic mass unit is defined as 1/12 the mass of a carbon-12 isotope. 1/12 of the mass of a carbon-12 isotope. In other words, one atomic mass unit ends up being equal to, I believe the number is 1.67. Sorry, 1.66 times 10 to the minus 27 kilograms. Gives me that conversion factor on my data sheet. It's rare that I'd have to use that, but just like every once in a while I have to convert electron volts to joules and grams to kilograms, okay, every once in a while I might have to convert atomic mass units to kilograms. Here's the rule though. Whatever units you're in for mass, what units do you want to be in for mass? Kilograms, right? If in doubt, get to kilograms. Now, how would you do the conversion? Well, we know this, right? One atomic mass unit is 1.66 times 10 to the minus 27 kilograms. 3.2 atomic mass units is x kilograms, and you'd simply solve for x there. Oh, here's the numbers that you have to memorize for tomorrow's quiz. But the good news is, I'm not going to ask all of those. I'll only ask 5 of them. Okay, got it? That's tomorrow's quiz. Okay, I want to do one question here that's going to use what we've learned about mass defect and binding energy combined with that chart that you just saw on the previous page, which of course you don't have to memorize. That chart is on page 881 of your textbook, by the way. And it's in the appendix. So if you have your textbook on your phone, then you'd have to download the appendix to get a copy of this chart. I've got a copy of it in my hand right now so that when we go to do this question, I don't have to keep flipping back to the page. But you can imagine how if I want the mass of barium-141, all I do is go back here and look for barium-141, and I would find the mass of it would be 140.914. Make sense? Like, you could get that information. I just don't want to keep flipping back and forth. That's why I've got it in my hand right here, so I can just take it right off the page. All right, so we want to find the energy released by the fission reaction. The example that we saw in class yesterday, in fact, except that we didn't have to calculate anything with it yesterday. Tell me where the energy released in this reaction comes from. 2 words. I asked this exact same question 10 minutes ago. Where does the energy in this reaction come from? Julia? Mass defect. So if we want to find the energy that's released here, then we better get the mass defect. What's mass defect mean? In the context of a reaction here, not in the context of a single nucleus. Yeah. Yeah, the difference in mass between the parent and the daughter nuclei. So the parent is on the left-hand side, the daughter is on the right-hand side. If we want to find the difference in mass between the parent and daughter, then we better find the mass of the parent and daughter and then subtract them. So here's the strategy here. Get the mass, get the total mass of the parent nuclei. Get the total mass of the daughter nuclei. Then subtract them to get the mass defect. And then find the binding energy by saying E is equal to mc squared. Make sense? Let's get the mass of the parent nuclei. Uranium-235, if you look back to that sheet, has a mass of 235.043930 atomic mass units. A neutron has a mass on that sheet, the previous page, of 1.008665 atomic mass units. Those aren't hard numbers to find. We just look at this table, read it straight off the table. Now, on the right-hand side, the daughter nuclei, barium-141 has a mass of 140.914412 atomic mass units. Krypton-92 has a mass, again, from that sheet, has a mass of 91.926. 151 atomic mass units. And a neutron, well, there's 3 of them, so it's 3 times 1.008665 atomic mass units. In order to get the energy released, you need the mass defect. We've got the mass of each of the individual isotopes, so what we need to do now is get the total mass of each side and then subtract them to get the mass defect. So Kyle, and over this way, is going to find the total mass of the parent, that's the blue ones. And then Eve, and over this way, you guys are going to find the mass of the daughter nuclei, that's the green ones. So on the blue side, we get 236.052595. Thank you. So that's the mass of the parent. Let's get the mass of the daughter nuclei here now. Eve, you got the mass of the daughter? Hold on for 1 sec here before you give me that number. Okay, prediction. Bigger or smaller than 236.05? Smaller, because we lose mass. If we have energy released, then we have to have lost mass. Okay, Eve, what was it? 8.6866389. Do we agree with those 2 numbers, guys? Those are right? Did we lose mass? Yeah, of course we did. Did we lose very much? No. That's your first indication that those numbers are probably right, because the right-hand side is smaller, but not very much smaller, and it shouldn't be very much smaller. Okay, let's get the mass defect now. By the way, we're in atomic mass units. Ultimately, we want to be in kilograms, but why haven't I converted to kilograms yet? It's way more work, right? Let's get the mass defect and then convert it to kilograms, right? So we only have to do it once. What is the mass defect there? 236 minus 235. Point whatever. Yep, Emma? 0.186. 206, thank you. That's in atomic mass units. Now we have to convert that to kilograms. So I'm going to say 1 atomic mass unit over 1.66 times 10 to the minus 27 kilograms equals 0.186206 atomic mass units divided by x kilograms. So let's get the mass defect in kilograms now. I'm going to do that by, that gives us 3.091 0.096 times 10 to the minus 28 kilograms. That's our mass defect in kilograms. And now it's easy. We want to find the energy released. It's just simply that number times the speed of light squared. And when we do that, we multiply that by speed of light squared, we get 2.78 times 10 to the negative 11 joules. Or we can convert that to electron volts, right? 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. Here's the questions that I want you to work on for homework tonight. Page 819, questions 1 to 3. Okay, sounds like a lot if we have to do that 3 times, but really you don't actually have to do it 3 times. You have to do it twice. This is really 2 questions. The first one, they give me the reaction. They want me to find the energy release in exactly the same way as I just did. Second question, they actually want me to balance an equation. We know how to do that. That's going to go pretty quickly for you. In the third question, they want you to find the energy released in the second one. So really it's 2 questions with a balancing one tossed in there, which is not very much work. Make sure that gets done, please, tonight. I want to do one more question here right now, though, before we move on to the next topic. This is finding, 2 more questions. The first one is just a balancing thing, which will help remind you, refresh your memory as to what to do with question number 2 there in your homework. And then the second one is to find some energy that ends up being released somewhere. 1939, 4 German scientists, Otto Hahn, Lise Meitner, Fritz Strassmann, and Otto Frisch made an important discovery that ushered in the atomic age. They found that uranium, after absorbing a neutron, splits into 2 fragments that each have a smaller mass than the original nucleus. This process became known as nuclear fission. All right, they didn't tell me anything that I either didn't know already or that I needed to know there. There are many possible fission reactions that can occur, 2 of which are shown below. The first one is exactly the reaction that I gave you as an example, and the second one is different. Uranium-235, but it forms something different. Notice they give it to me in 2 steps, though. Neutron plus 235 uranium gives me 236, which gives me barium. They just split it up, right? I told you that the uranium absorbs the neutron and then splits up. We just wrote it as one reaction. They've written this 2. No worries. What's the value of X in reaction 2 here? All right, what do we have on the left-hand side? 236 and 92. What do we have to have on the right-hand side? 236 and 92. Well, what do we have here and here? 140 and 92 gives me 232. 54 and 38 gives me 92. What am I missing? What am I missing on the right-hand side? Well, we can't have 4, 0, right? So what do we end up having? 4 times 1, 0. 4 neutrons. So what's the answer to this question? A. The value of X is 4. Does that make sense? That's a balancing thing, and that's one of the things that you're going to have to do, or it's the thing you're going to have to do in question number 2 in your homework. Now, the last one that I want to do, this talks about mass defect, but this is not the mass defect in a reaction. This is the mass defect in a nucleus, in a single nucleus. Remember the difference? The difference in mass between what you end with and what you start with for the reaction, the difference in mass between the nucleus and the nucleons in the context of a nucleus. So here's what I want to do. This is the mass of the nucleus. I want to find the mass of the nucleons. What am I going to do? Add these two numbers up? Mass of a proton plus the mass of a neutron? Is that what we do? Plus the mass defect? Well, we've got to find the mass of the nucleons and then subtract the mass of the nucleus and the mass of the nucleons to get the mass defect, which is what we're looking for here. I don't want to just add these up. How come? Yep. No. I want to find the difference in mass between the nucleus and what makes up the nucleus. What makes up this nucleus of uranium-235? It is not a proton and a neutron. What is it? A proton and neutron don't make up a nucleus. What makes up a nucleus? How about 92 protons and 143 neutrons? What you got to do here is multiply 92 times 1.6726 times 10 to the minus 27 and 143 times 1.6749 times 10 to the minus 27. Get the mass of the nucleons, right? Because there's that many protons and neutrons in that nucleus. And then subtract it from the mass of the nucleus itself. That's going to give you your mass defect, and then you're going to multiply that by c squared to get the energy released, which is question 168. Does that make sense? Yep. You'd add these two together, right? You multiply these, you'd multiply these, and then you'd add them up to get the total mass of the nucleons, and then you subtract the mass of the nucleus itself. It should actually be the other way around. Mass of the nucleons minus this, but it doesn't really matter. You're going to get the same number. Okay? Yep. I'm sorry, say it again. No, no. The mass of uranium-235 would not be on your data sheet. Oh, no, but you've got a periodic table, right? And on your periodic table, you would see that there's a atomic number of 92. So you'd know that there's 92 protons as a result of that. And then you just say 235 minus 92 gives me 143 neutrons. Make sense? So not on your data sheet, but on your periodic table, you get the number of protons, and then you figure out the number of neutrons from that. Does that answer your question?